Hello, everyone. Today I'm going to speak with you about organic chemistry, just kind of drill into what's to be expected next semester should you continue, and just some sort of general principles underlying the, or just really an intro, essentially. So carbon is central to living matter, as well as many inanimate objects. So some of the inanimate objects that you can all see are kind of essentials here. So anything from drugs to foods. So clearly we're not going to eat anything that's essentially living, maybe some things like, bacteria or what have you. But so all these are going to be carbon-based polymers. So things you're not going to eat, like, for instance, types of plastics, composite decking, and even some biomacromolecules, right? So the things that contain protein, as well as cellulose, right? So your carbohydrates, etc. Fuels, so all of your hydrocarbons, all your alcohols, those are all, of course, consist of carbon, as some central sort of construct. And then some cleaning products as well. Not particularly bleach, not something you want to ingest like somebody suggests. Anyway, millions of compounds cataloged and in use. Think of carbon as the silly putty of the material world. When I say that, I'm not saying that's literally what silly putty is comprised of. I'm saying that, it's the most manipulative, or I guess one that you can manipulate the best. So the best way to do that is actually functionalized by electronegative groups, because if you have just carbon to carbon, most of the times those are very, very stable bonds. Okay, so in other words, to break those bonds up requires an appreciable amount of energy, oxidation, things of that nature. So again, hydrocarbons are not so reactive, mostly just oxidize or uncontrollably radicalize with halogen gases. So these are kind of shotgun approaches, if you will. They're not very contained. Okay, so let's talk about some saturated and unsaturated species. So the best kind of analogy I can give to this, or something that's more of in a layman's understanding, is saturated versus unsaturated fats. Saturated fats, for instance, butter or something like coconut oil, right? So those are all actually esters, but they have long fatty acid or hydrocarbon chains. Okay, so these are all hydrocarbons. Okay, as well as unsaturated species. So if you have something that's mono, di, tri, unsaturated, mono triglycerides, right, in your blood. So all these types of mixtures of different fats, for example, are have different sort of physical properties, as well as chemical. Okay. Now, saturated hydrocarbons, when linear, stack neatly via van der Waals forces. So I'll get into linear versus branch constructs later, or cyclic. Okay, so in other words, you can kind of think of lawn chairs that it'll stack one on top of the other. They have more kind of uniformity together as opposed to just being by themselves. Okay, now unsaturated hydrocarbons, when linear, actually stack or do not stack as neatly. So you can think of kinks. Not some things that most of you'll discover later, but more of, is every single molecule going to stack neatly? And it's not going to be the case, because you're going to have some going in one some tails going in one direction as opposed to the other, and they're not going to really conform in the same way. So that's why you see something like, let's say, olive oil. So we'll put butter up here for an example, and then we'll put olive oil for another. So olive oil is a liquid at room temperature. It might do something called supercooling. So what that means is, you'll see like little crystals that may pop out over time. That's a natural occurrence. Of course, if you just shook it up, you'd give some energy to it and go right back into being a liquid. Okay. Now this may also affect the boiling point or smoke point. So for let's say if you're looking to saute something at a really high temperature, you would use grapeseed oil or something with a lot of alkene species rather. Okay, so sorry about that. I'm just kind of slipping here. Cyclic compounds like benzene and pyridine have different properties, electronegativities, and reactivities. So benzene and pyridine, which you'll see below, they have pi bonds sort of scattered around them and resonating at all times. So there's sort of an electric current, if you will, that's running along that kind of construct of the sigma bonds. Okay, so there's different electronegativities, of course, so that means they're going to have different sort of properties, as well as reactivity. So those pi bonds can actually reach out and establish a bond with something else, with the aid of a catalyst or something else. So for instance, benzene, which is typically thought of as being pretty stubborn in terms of reactivity, because again, these pi bonds are constantly resonating, right? Flipping over from one bond to the next. So it's going to go double, single, double, single, double ad nauseum. If you were to react that out with bromine 2 and then iron bromide as a catalyst, so this would be a catalyst, like you learn in chapter 13, you are going to push the reaction forward and get what is referred to as a substitution. Again, I'm not expecting you to know this. This is just sort of something to eventually look forward to. You move on with organic chemistry. So in other words, this is reactive. You're not going to see the same kind of reactivity or the same control reactivity with just an alkane species that is saturated. Okay, repeatedly writing carbons and hydrogens gets a little tiresome. So here's where line structures come in. So if I didn't have line structures to teach a whole year worth of organic chemistry, it would take 2 years. It would literally take that long. So each corner and end is representative of a carbon. But remember that each corner and each end must have a full octet. So that means you have to assume where the hydrogens are if they aren't indicated. So we'll get into that in a minute when I go over some of these examples here further down. Linear compounds may or may not have indicated carbons. So that's or indicated hydrogens. Okay, sorry about that typo. Okay, so now examples. So this right here is what is referred to as pyridine. Notice how nitrogen is right here. It has a lone pair. So we're just gonna this is just something of habit that I put there as sort of a bubble around those 2 dots. Kind of makes it look like a ghost figure, if you will. Okay, so you have a nitrogen and then you have 5 carbons surrounding it in a cyclic fashion. Okay, so this is going to be a very stable molecule, again, because there's going to be a resonance stability about these pi bonds flipping over from bond to bond to bond to bond. Okay, and how that would look, notice how there's a total of 4 bonds about each carbon here. There's going to be a 3 about nitrogen because nitrogen has a valence of 5, so 1, 2, 3, 4, 5, and then it shares an electron with the neighboring adjacent carbon. So in other words, you're going to have a full octet about this nitrogen as well. So 1, 2, 3, 4, 5, 6, 7, 8 valence electrons. The only thing that's sort of counter to that is the hydrogen, which is just going to be a duet. You're filling up an s orbital. Okay, so with that said, this is what pyridine is going to look like. Notice how I didn't draw it exactly like how you see on the left because of the double bonds shifting over. That doesn't really matter. It's going to be the same molecule, seeing as it's a flat planar structure and there's no other substituents about it to make it look different. So this will resonate back and forth if you remember your resonance structures. Okay, so it'll just look like this. So that is a direct representation of what you see right here as a line structure. Again, the hydrogens are not indicated in this particular case, so this is kind of the fastest way to go about things. Let's take this next example here. So this is 2-methylpropane. So I wasn't expecting you to know that, but nonetheless, the main structure, the longest chain here is 3. So pro is the prefix for 3, so propane. And then methyl, if this were standalone without this stuff right here, if it just had an extra hydrogen, that would be a methane, right? A methane molecule. So this is what is going to be referred to as a branch that we'll talk about later. But just for the sake of the exercise of drawing the line structure equivalent, there's going to be, it sort of looks like 1, 2, 3, so almost like filling in the inside of a triangle. So remember that each one of these points at the end is supposed to represent a total of 1 carbon and then 3 hydrogens. If it's terminal like that, that means it's a methyl group, right? But the whole construct is propane from the longest count of carbons that are contiguous. All right, so notice how I don't put the hydrogen here either, okay? So this is exactly a line drawing or line structure representation of 2-methylpropane. Okay, so next step here is you see, or the next example you have here is trans 2-butene. Okay, so but stands for 4 for prefix. So 1, 2, 3, 4. Count of 4. Okay, and notice how it's trans. So if that's the case, then if it were cis, the CH3 group would be sitting up top and the hydrogen would be at the bottom. We'll get into sort of really baby stereochemistry a little bit later. But so this is a line structure representation of 2-butene that's on the left here. Okay, so in other words, these hydrogens, again, are just sort of assumed. Okay, and then lastly, we have a linear compound here. So we have, let's see, it would be 1 propionamine. So this would be, and again, I'm not expecting you to get the nomenclature down. What I am expecting you to do is to at least choose the correct line structure. Let's say if you had this on a particular test. Okay, so I'm not going to do anything super elaborate, right? I'll draw something about this difficult, and you have to draw it out or pick the right line structure equivalent. Okay, so let's take a look at this. So notice how from the previous example I had 1, 2, 3, 4 carbons. So in other words, each sort of point is where a new carbon exists. So here is the terminal methyl group that you see here on the left. One, two, three, and then that third carbon's directly attached to nitrogen. Now, how the numbering would go one, two, three in terms of locators. Okay, and I'll get into locators in a minute. Locator numbers, because you're going to have different location sites where things are going to branch off. So in other words, this is a branching group because you're thinking about carbon as the main structure. Okay, so carbons can also branch. So that's really one of the more attractive or stable features of an organic molecule, or one of the attributes of its stability is its ability to branch off into, potentially 4 different ways, or tetrahedral, as you may know. So carbons can also branch. So let's just take a household antiseptic. So this is what is referred to as isopropyl alcohol. Again, something you'll see in the store, maybe about 70%, 90%. The rest being water. Okay, so isopropyl alcohol, or 2-propanol, or IPA for short, not the IPA you drink. So this molecule is miscible. In other words, it's mixable with water. Again, like I said, you can buy 70% solutions, 90% solutions. But longer hydrocarbon chains are not miscible with water. So that's to say, if you had, let's say, 2 more carbons hanging off this side and 2 more carbons hanging off this side, it's not going to be as soluble in water. And the reason why is because, remember that this can act as a hydrogen bonding donor as well as a hydrogen bonding acceptor. The fewer of these hydrocarbon chains that you have, the better it is to solubilize with water and have that hydrogen bonding, which is a strong intermolecular force. Okay, so let's take a more elaborate hydrocarbon like the following. So this is 2-methyl, 7,1-methyl propyl undecane. Sounds like a mouthful. It is. Okay, but the reason why you would use this kind of systematic sort of nomenclature approach is because, if you were to swap this methyl over here, this this isobutyl group or methylpropyl group, more formally, somewhere else, you're going to have a different numbering scheme. So in other words, you're going to have a different connectivity. Okay, I wasn't expecting you to name that. It's just kind of more an extreme example or advanced example here. Now, this compound could have potentially hundreds, if not thousands, of isomers. So what that means is, again, you will have different connectivity. You may have, you won't have any isomers that are rings, but you'll have, different sort of linear branching, whatever have you, compounds, which would have the same molecular formula. Now, if we were to look at this from a empirical formula perspective, all right, we could say this is C8H18. So C8H18 is actually divisible by 2 as well. So going from C8 to H18, we'll say to C4H9. So this is the empirical formula of this actual molecular formula. Again, this doesn't tell you very much about, in fact, it tells you nothing about the actual connectivity. And if you were to try to draw this or write this out, especially if you were to type it out, it would take you forever instead of actually drawing it like a line structure. So this is going to be the empirical formula. So remember, the empirical formula is just sort of a proportional count of carbons to hydrogens to oxygens, nitrogens, or whatever all is a constituent of that particular formula or molecule itself. Okay, IUPAC nomenclature has distinct descriptors for branching groups and functionality. Okay, so depending on if it's a ketone or an aldehyde or a carboxylic acid or, nitrile, that's all going to make a difference in terms of how things are named. Am I expecting you to know that right now? Absolutely not. That takes, half of the first semester to get through. Okay, so some isomers can look very similar, but different connectivity means different compounds. So that can also mean different physical properties. So if you have more branching here, there's less likelihood that you're going to have some kind of stacking, right? It's going to be a little bit more disordered. It's like trying to see, let's say if I showed up back to, class or something, and you saw me with, let's say I had all of my, pieces of my arms and my legs all reattached to my torso, but instead of having joints or whatever, I would just have single bones sticking out of my torso. It would look a little bit more disfigured and less ordered. I guess it's sort of a macabre way of looking at things, but hey. All right. So, as said before, naming alkanes is systematic. So there's the main chain, so the longest contiguous carbon. You can say that's my head all the way down to my toes, right? And then my arms on the left and right are branches or side chains, right? So I got my branches are my left and right arms, right? And then a side chain or something that's derivative of that. Let's say I could wear a glove or I could wear, I don't know, whatever. So that's a different kind of functionality. Or let's say I could use a chainsaw or an axe or a hammer or, a screwdriver. That would be a kind of side chain or functionality that I could use. All right, numbering of locator numbers must be lowest. Okay, so in other words, wherever you're mentioning the side chain or the methyl or a branch of any particular kind, you have to go with the lowest locator numbers. So in other words, this is going to be the longest chain. It's going to go 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12 carbons in length. So that's not going to be undecane. That's going to be dodecane. Maybe I drew an extra. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Yeah. Okay, so that's going to be dodecane. And notice that ANE suffix, that's just going to suggest that that is the main chain. Okay. Methyl branch here, so that YL suffix is just to state that that is actually a chain that is not part of the main, or sorry, a branch that is not part of the main chain. So you have methyl branch here as well, and then a side chain. So again, this could or could not be an electronegative species, but when you're looking at a branch, you're looking for something that has the longest carbon count. So 1, 2, 3, and this would be really more of the side chain if you think about it. So 1, 2, 3, that's going to be a propyl. So propyl. And this is going to be a methyl. Again, YL is the suffix to tell you that you have a branch that's coming off of a main construct or main chain. Okay, so is the numbering scheme going to go from right to left or left to right for locator numbers? Okay, so if you start from here, you're going to go 1, 2, 3, 4, 5, 6. So it's going to be the first locator number. 6, 7, 8, 9, 10, 11. So 6 and 11, pretty high up on the scale out of 12. So in other words, you would probably want to start from the right going left. So that would go 1, 2, 3, 4, 5, 6, 7. So 2, 7, blah, 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 blah. Okay. Now, find the main chain and branches of the following. So I'll give you a few minutes to do that. Just be sure to pause. Okay, so the main chain that you see right here, you could either start at this side or you could start at this side, but it's all going to be a 4-membered main chain. So in other words, you would go 1, 2, 3, 4. You wouldn't go 1, 2, 3 because 3 would be larger or higher than 2. So this would be 2-methyl. Again, there's just one carbon there, so meth is just a single carbon. 2-methyl butane. Okay, so 1, 2, 3, 4. Okay, so this one's symmetrical, so what you don't want to do is start at one of these. You would start at, say, 1, 2, 3, 4. Whoops. 4. My 4s and 5s off today. All right, so a count of 5, going from left to right, the longest contiguous carbon chain there. So you're going to have a 3,3-dimethyl. Okay, so there's not 1 but 2 methyl groups hanging off of that 3 position. So it would be 3, 3-dimethyl pentane. So A and E, again, the suffix for the main chain. Pent is to represent 5, like a pentagram, right? Okay, so let's take a look at what we have here in the next option. So it's tempting to think that everything is going to be at the bottom as the longest chain, but that's not the case. Okay, so you have a junction right here where you have 2 different types of branching chains or groups sticking off of that carbon. So if you're going to go from left to right, or sorry, from right to left, it would go 1, 2, 3, 4. If you're going to go from left to right, you would go 1, 2, 3. So you would want 3-ethyl, 3-methyl. So it's typically going to go in alphabetical order. So it's going to be 3-ethyl hyphen 3-methyl. 1, 2, 3, 4, 5, 6. So that's going to be hex. Like I put a hex on you. Hexane. Okay. All right, last one. We have longest carbon chain count of 1, 2, 3, 4, 5, 6, 7. Okay, so that's going to be heptane. Heptane. Okay. All right, and then we have, if we counted from this side, it's going to go 1, 2, 3, 4, 5. So it would be 4,5-dimethyl. But going from right to left, you would go 1, 2, 3, 4. So 3, 4, 3, 4 hyphen dimethyl heptane. Sorry about the space there. Okay. So we assign the appropriate locator numbers for the branch. So in other words, 1, 2, 3, 4, 5, 6. Okay. 1, 2, 3, 4, 5, 6, 7. Okay, so if you want to just take inventory of all the different prefixes or something to kind of, I guess, bookmark for your exam, Table 19.3 has prefixes for a count of branch and multiple choice carbons. All right, so unsaturated species, onto alkenes and alkynes. So alkenes are can be cis or trans disubstituted. So before I said this is going to be trans 2-butene. Right. Cis 2-butene would look like this. So that means both of these higher order carbons. So carbon's going to be heavier than hydrogen, right? Remember, you have to assume these hydrogens on opposite ends to complete a full octet for each carbon. It's going to be methyl here, methyl here. So this is going to be cis 2-butene. Okay. E and Z isomers. So this is what is referred to as having stereochemistry, right? So in other words, these are what are referred to as diastereomers of one another. Again, not really expecting you to know that, but you're going to have a flip of these. You know, if you had some higher energetics, this one's going to be more stable than this one, just because these two methyl groups are going to be in such close proximity, and they're going to be bumping into one another, and this is going to be more relaxed and less less clustered, if you will. Okay, so E and Z isomers. So let's say E is more along the line of trans. So this would be E. And for the longest carbon chain, you'd have 1, 2, 3, 4, 5, 6. This is somewhat symmetric. So, in other words, 1, 2, 3. 1, 2, 3, 4. So this would be the first locator number because, again, this branching group is a methyl, right? So in other words, the alkene or alkyne is going to be a part of the main chain. Okay. Now, so you're going to have hexene, hex 3-ene, because again, you want to have the lowest locator number, so you're going to have 3 methyl. This is the methyl. Hex 3-ene. Now you could have a diene, you could have a triene, tetraene, whatever. So if you just have this one stereo center, in other words, you're going to have just the E or Z. So Z, the reason why this is E is because this is opposite, okay? So the ethyl group is going to be a higher order than the methyl group, okay? And this ethyl group is certainly going to be bigger than the hydrogen. So in other words, whatever's directly attached to that alkene or CC double bond is going to have the highest priority in terms of atomic weight. Okay, so the Z isomer of this would look like this. Okay, so this would be Z, and the way I keep this straight is E is for opposite, is in opposite sides, and then Z is on the same side. Kind of cheesy, but you know, kind of sticks. All the dumbest puns really stick in this class, by the way. Okay, so 3-methyl hex 3-ene. Okay, so the location of the alkene didn't change. It was just the configuration of where that ethyl group is with respect to what's on the other side of that alkene. Okay. All right. So substituent, just to clarify, is anything other than hydrogen bound to a carbon. So, for instance, let's go back. So some of these are hydrocarbon substituents, right? So it's not hydrogen over there. It's a carbon that's represented. So this is an alcohol substituent, so it's not a hydrogen that's right there that you'd normally see in a hydrocarbon. Okay. So alkynes do not have stereochemistry since their geometry is linear. Okay, so that previous example that I showed you, I dropped everything on the floor here. So this line structure is drawn, one dimension from left to right, right to left, whatever. Okay, so in other words, this triple bond is going to keep everything fixed 180 degrees side to side. Okay. All right, so some natural products extracted, so natural products, the definition is essentially extracted organic molecules from a living organism or dead organism, right? Have these functionalities. Okay, so they have alkynes, they have alkenes. So if you want to think of certain types of pheromones, or if you want to think of certain types of sterols, right? So cholesterol or whatever, those are all going to have some kind of alkene groups. Maybe they're cyclic, maybe they're linear in construct, or jagged, if you will. Okay, so some polymers possess them synthetically as well. So if you read through your text in chapter 19, you might have seen, linear, things that kind of pack really well, like high density polyethylene versus low density polyethylene, where there's a lot of branching. Okay. So some plastics or polymers are recyclable, as others are not. This is due to the functionality of the branching branching off. So you might have seen polystyrene, cellulose, which is just stuff that you would get from wood, right? So in other words, paper products, Kevlar for bulletproofing. HDP, which stands for high density polyethylene, like I just mentioned, versus low density, which is branched. Polyvinyl chloride, which is a very robust sort of plastic that's used in piping, and as well as siding and things of that nature on your house. And then Teflon. So this is a type of plastic that is very much resistant to things that are very corrosive, and will degrade some of these other things that you see here. So, in terms of things that are recyclable, if you don't want to live around a landfill, it might be good to practice recycling. I kind of got it down when I was 8 years old, 32 years ago almost. Yeah. So, do what you do. Okay, aromatic systems are stable pi systems with most, if not all, carbon constituents. So, like I said before, with pyridine, you saw that there was that nitrogen. Okay, so one nitrogen in 6 elements. All right. 6 elements about the ring. Hydrogen isn't going to be a part of a ring, right? It's going to form a duet, so that means it's only going to be singly bound to something. Okay. So aromatic systems always have a count of 4n plus 2 designation. Again, I'm not expecting you to memorize that. Just know that there's going to be some pi bonds that kind of flip around and keep everything stabilized. Okay. So aromatics, just to make sure we're not confusing things in terms of semantics here. Aromatics, that doesn't necessarily mean that certain things have a smell. These typically have to have some kind of smell, but that doesn't mean that everything that smells has to have this, right? You can smell acetone. You can smell a lot of different compounds that are not classified as organics, okay? So pyridine is an organic, furan is an organic, benzene, which is a pretty common organic, naphthalene, which you would find in, let's say, mothballs if you're trying to preserve some sweaters and keeping them through storage whatever the duration. This is toluene, so this is a branched version of benzene. So this is a very common solvent in certain types of chemical reactions. Trinitrotoluene, so if you've ever driven through the tunnel, you can sort of thank that molecule for it being there and basically borrowing a big hole into the earth for you. And then there's phenol, so this is a type of solvent that's actually used in trying to isolate DNA and RNA and things of that nature, or proteins. Okay, so if you're doing some kind of DNA extraction or RNA extraction. Okay, electronegative functional groups affect reactivity and state of a compound. Now, I'm just going to go over a few of these for examples, and then we're going to look at some examples that I'm going to have you match, and then a more elaborate molecule where I'm going to have you pick them out. Okay, so first up is going to be ethers. Diethyl ether, which is a common organic solvent, it's a polar aprotic solvent. This is diphenyl ether that's right here, a little bit less common. So notice how oxygen is singly bound to 2 carbons, okay? So oxygen likes to keep its electrons, as you well know, second most electronegative element. Okay, and then on to aldehydes. So aldehydes are CO double bond species or carbonyl species. So this is formaldehyde right here. So just a common name. So these 2 hydrogens that are here on the side are going to differentiate from, let's say, one of these methyl groups, which is, this is referred to as acetaldehyde. Okay. Again, I'm not expecting you to memorize all this. This is just for your own means of trying to identify. Now, aldehydes, if you're looking for the commonality here, you can see this C double bond O H. Okay, so that's sort of written shorthand as CHO. If you were to write out a molecular formula. Okay, so, and then same thing goes for ethers. If you were to identify the actual functionality, you would circle this, carbon to single oxygen to single carbon bonding. Okay, and then ketones. So similar to aldehydes as previously discussed, but you have 2 carbons attached at both ends of that C double bond O carbon. Okay. So this is acetone, which is common in nail polish remover. This is what is referred to as acetophenone. Okay. Amides. So these amides that you see here that are in brackets, these are what are referred to as carboxylic acid derivatives, just like an ester would be. So carboxylic acids are going to look like this, if you recall from so for instance, acetic acid is a carboxylic acid. Okay, so notice how carboxylic acid and their derivatives all have electronegative groups directly attached to that carbonyl. So esters, amides, and carboxylic acids, again, all have something electronegative directly attached to that carbon, not just a carbon itself. Okay, so amides here, as you see, these are actually bonds to form a peptide chain. So this R group here and R group here are what are referred to as residues. If you get into biochemistry and things of that nature, you'll see that some of these residues sort of differentiate and make up different types of proteins, based on their folding and what kind of intermolecular interactions they can have. Okay, so this would be referred to as a biopolymer or biomacromolecule. Okay, so let's sort of put these into subclasses. So aldehydes and ketones, those are going to be carbonyls without an electronegative group attached to that carbonyl. The amides, esters, and carboxylic acids, again, those are all going to be carboxylic acid derivatives and have an electronegative atom directly attached to that CO double bond. Then you have another singly bound species, was referred to as amines. So this is ammonia, which isn't necessarily an organic compound. It's rather an inorganic compound, most simple amine, if you will. And then you have, okay, so on the last page of your worksheet, you'll see sort of a matching exercise as well as a more elaborate molecule. I kind of goofed and didn't press play when I recorded everything, so just go ahead and work through that, and then pause for a minute, and then we'll get into the final. Okay, so for ketones, it's going to be D. Remember that ketones have a carbon on each side of the carbonyl. Aldehydes are going to be C. Remember that aldehydes are terminal, so that means that hydrogen is going to be there on the end where it can't branch. This could be a methyl, this could be a ring, this could be a phenyl ring, it could be tons of different things. An alcohol is going to be E. So it's this, remember, C single bond O, not C double bond O like you see for these two. And then an H directly attached to oxygen. So you can think of this almost analogous to water, which is a very simple alcohol, inorganic. Okay, so an amine is C single bond N. So this is going to be methylamine. And then alkyne, just by process of elimination here, is going to be CC triple bond. So in this case, it's going to be a terminal alkyne because you have a hydrogen on one end of it, of the triple bond. And so no further derivatization can occur unless you remove that hydrogen and put something else in its place. Okay, so let's go over the actual molecule at the bottom of what's in your transcript. Okay, so this is going to be an amine, again, CN single bond. It's going to be different from an amide. Okay, so an amide is going to have the nitrogen directly attached to carbonyl. So amines and amides are not interchangeable. Just like ether and esters are not interchangeable. So let me cross this out, make it legible. Ether is not interchangeable with ester. So an ester is going to look something like R being some kind of alkyl group or something like that. So again, CO double bond with a single oxygen attached to it, and then some kind of carbon species on the other side. A ketone, again, is when you're going to have a CO double bond with a carbon on the left, carbon on the right. Phenyl group is just going to be an aromatic six-membered carbon ring. Phenol is going to be different from phenyl, seeing as OL is to indicate that there's going to be some kind of alcohol. So this is a phenol derivative, whatever this is. Okay, and then alcohol is when you have a COH, again, C single bond O, single bond H. And that's sort of representative of water. Instead of having a hydrogen here, it's going to be a carbon. Okay, so ether group, ketone group, alcohol, phenol, phenyl, and then an amine. All right, I hope this was informative, and hope you learned something from it. And be sure to have a good break if you're not getting into organic over the summer. But, you know, if you do decide to enroll in the class, I'd definitely recommend doing things in a quick manner, and not for the sake of, sort of peeling the painful Band-Aid off in, a quick fashion, but you're really focused on that and nothing else, or at least it would be advantageous to your grade if you just focus on organic and not anything else. All right, so have a good one. If I don't see you, take it easy.